Welcome to 11.5, Arithmetic and Geometric Series. I want you to look at example 1 and think about what type of series that is, just as a quick review. And if we look at it, we know that it's arithmetic because we're going up by a constant of 3. But I want to talk about series today, and the word series, remember, is adding things up. We use sigma notation, if you remember right, from a couple, or actually yesterday's lesson. So we're going to do something different today. We're going to derive some formulas other than using sigma, just to show you some algebraic concepts. So when we look at example 1, we're adding up a number of terms. Now we know that conceptually you could just add these up with your calculator or in your head pretty quickly, but I wanted to use this example so that we can kind of wrap our brains around numbers. So one other idea here is if we took 1 and we added 1 to 28, we'd get 29. And if we did that for the next pair of terms, we get 29. If 4 and 25, we'd get 29. Welcome to 11.5, Arithmetic and Geometric Series. So today what we're going to talk about is alternatives to using sigma notation from the previous lessons. And in example 1, you'll notice that we have an arithmetic sequence. Now, it's not very long, but I kept it short so that you can kind of conceptualize what's going on here. So if we were to add up all these terms and find the sum, that would be the most obvious way. But if we kind of use some alternative methods and we look at some relationships, we'll notice that if we add 1 and 28, we get 29. And if we work our way in, we take 4 and add 25, we get 29. And if we take 7 and 22, we get 29. And if we take 10 and 19, we get 29. And then lastly, if we add 13 and 16, we get 29. So adding pairs of numbers as we work our way in gives us a sum of 29 every time. Well, what you should notice about that is that there are 5 sets of 29. Well, in this problem, n was 10. There were 10 numbers. So essentially, we've come up with a formula, and it's called the partial sums of an arithmetic series. So we basically came up with the sum of n numbers is equal to the number of numbers divided by 2. And all we have to do is take the first term and add it to the last term. Now there's an alternate form for this that I really never use. I just kind of, if I need it, I just kind of plug and chug. But I want to show you another alternate form in the book. If we take this formula that we just found out, and we take out t sub n, and we replace it with what we learned the other day, t1 plus n minus 1 times d. Well, then what we get is an alternate form. We're going to get s sub n equals n over 2, parentheses, 2 t sub 1 plus n minus 1 times d. Sometimes this can be helpful, but like I said, I really don't memorize that. I just kind of use the formula from the previous day, and I just stick with the sum, the basic sum of arithmetic series formula. So let's try example 2. How many terms of the sequence 5, 7, 9, ... must be added to get 572? Well, what we want to do is avoid guessing and checking. We want to use the formula. So the formula says that the sum is 572. We're trying to figure out n, which is the number of numbers. And we know that the first term is 5. And if you use the shortcut method that I talked about the other day, we can quickly write down the pattern for this. Remember, the y-intercept, if you think about it like a line, would be the number before that. That would be 3. And the slope is 2, so this would be 2n plus 3. So then we combine like terms, and we get 572 equals n over 2 times 8 plus 2n. When you get here, you have to figure out what do you want to do. You got to make some decisions. Well, what I'm going to do is go ahead and distribute to get 8 times n over 2 is 4n, plus 2n times n over 2 is going to be n squared. Now I'm going to rewrite that and it's basically solve for 0. So I get 0 equals n squared plus 4n minus 572. Now remember, you have your calculators. This would be pretty difficult to factor if you didn't have your calculator. So use your calculator, help yourself out to factor. I want you showing the method of the algebra. So you get the quantity n minus 22 times the quantity of n plus 26 equals 0. If you were to solve that, normally you would get n equals 22 and negative 26. However, because we're dealing with sequences, very similar to the conversation the other day, if there's a geometrical figure, etc., well, sequences have to deal with the number of numbers in a sequence. So we cannot have that be negative, so n must be 22. Well, how do we determine the nth partial sums for a geometric series? For time, to save time in the video, I kind of went ahead and showed you the proof of this really quickly, but I'll explain it. So if we had some partial sums of a geometric series, S sub n, and we basically said the first term was a, so I'm going to let t1 equal a because it gets a little messy if we have too many subscripts and superscripts, so I took out t1 and put it in a to make it cleaner. So a would be the first term, and then remember, you'd add the common ratio times the first term, and you would keep doing that. So like a plus a times r plus a times r squared plus a times r cubed, etc., all the way down to basically a to the r to the n minus 1, which is the general pattern of our geometric sequence that we learned the other day. So what if I took that whole entire first line and I multiplied through by r? Would you're allowed to do an algebra multiply by, and I picked r because it's the common ratio. Then you would get the second line that you see. Then in algebra we have two different equations. We can always subtract. So we're going to subtract the columns. So we're going to take the top column minus the bottom column, and you would get the third line, s sub n minus r times s sub n equals, and all the a times r's would cancel out except for a, and the last term a r to the n. So you'd have on the right side a minus a r to the n. Well, if I factor on both sides, I take out the s sub n on the left, I take out the a on the right, and then I solve for s sub n by dividing by 1 minus r. I'm dividing by 1 minus r here. I would get this formula. Well, that is the nth partial sum for a geometric series. And then I took out the a and substituted back in the t1, so it's using the terminology that we've talked about for the chapter. So let's try example 3. So find the sum of 34 numbers for the geometric series 7 minus 21 plus 63 plus, and then it continues on. So what we want to use is the formula. So we know S34 is what we're looking for. And we have to think about 7 is the first term, 1 minus, and then we have r, which is negative 3, and we want to raise that to the 34th power all over 1 minus negative 3. Now it's very important here that when we do this next line, our order of operations are sound. So we want to make sure that, think about this, we're going to do negative 3 to the 34th first. And the reason I rewrote this again was I want to make sure that you know, in the bottom we get 4, and you know in the top, that you have to do the power first, because if you don't and you distribute, this is the key here, you could end up changing your signs for the worse. So make sure you follow your order of operations. And when we do that math in our calculator, we get negative 2.92 times 10 to the 16th. Now look at example 4, and for time's sake I went ahead and wrote the first line of work. We have 5023.14 is the approximate value of a partial sum in the geometric series where t1 is 150 and the common ratio is 1.04. Find the number of terms that were added. So we set up the formula, and we're going to have to use our calculators, but we want you showing your work. So when we set up the formula, we have 5,023.14 on this side. I'm going to keep the 150. 1 minus 1.04 to the n. And I'm sorry, I realized I made a mistake up here when I wrote down the original notation. I should have had n. Inside the parentheses. Apologize about that. So on the bottom, we have negative 0.04. And then what I'm going to do is I'm going to multiply through by basically negative 0.04 over 150 on both sides. Because I want to basically essentially cancel these out. And what I'm going to get is negative 1.339504 equals 1 minus 1.04 to the n. So I'm going to subtract 1 to both sides, and I'll get negative 2.339504 equals negative 1.04 to the n. If we divide by a negative, we could think about, because that's a minus sign. Remember, that minus is not with the actual base of 1.04. So I'm divided by the negative. And then I have 2.339504 equals 1.04 to the n. Now I can rewrite using logs. So I could say the log of 1.04 of 2.339504 is going to equal n. What we're going to get is we're going to get n equals 21.67. So now think to yourself, n cannot be a decimal. It has to be an integer, right? Because this position. So would you leave it at 21 or would you leave it at 22? And really take some thinking here, because the sum has to be 5,023.14 approximately. So your gut would hopefully tell you to round up, because you need to get the sum. 21 wouldn't quite get it. Good luck on your homework.